Before we begin, this is the Optic seminar, and we are sponsored by OSA, SPIE, and IEEE chapters. So if you want to register for the mailing list of iOptics, or if you just want to unsubscribe your name from our mailing list, then you please fill out your name here with your email address. So I'll pass this around. And you just enter these information. And if you want to unsubscribe, write out some notes on the right so we know what to do. So next, I'll introduce Yafang, so to introduce more about the speaker. Thank you.
Hey, good morning, everyone. Thank you for coming to the seminar. Today, our speaker is Professor Worseman. Dr. Worseman is an assistant professor in electrical and computer engineering from here. His research team focuses on plasmonic and metamaterial devices and structures, nanotechnology, and semiconductor-based material system for mid-RI wavelength range. Professor Worseman received his PhD from Princeton, and he is a recipient of the NSF Career Award, AFOSR Young Investigator Award, and the 2010 Excellent in Teaching Award. Let's welcome Professor Worseman.
Thank you. Thank you very much, and thank you for the kind introduction and for inviting me here today to talk about my group's work. So in particular, what I want to talk about today is the title of my talk, which is Making Mid-Infrared Nano with Designer Plasmonic Materials. And I'm going to talk about how we can start thinking about using micron scale light at the nanoscale and what that means for sensing applications and for other sort of security and defense applications. Now, before I begin any of my talks, I always like to thank the people who actually do the work. In this case, is my research team, in particular my postdoc Stephanie Law, as well as my graduate students. And I work with a number of undergraduate students. I've listed my current undergraduate students here, as well as some of my former undergrads who contributed to the work I'm going to be showing to you. We also collaborate with a number of groups, both on and off campus. In particular, the group of Professor Podolsky, who does a lot of the theory work with us. And I'll be showing you some results from a collaboration with Professor Bill King's group here at UIUC. Okay, and these are our funding agencies. So to give a brief outline of what I'm going to be talking about, first I want to tell you why we might be interested in the mid-infrared. Okay, and what I'm going to be talking about today is essentially a field of optics that we call metal optics. So why would we be interested in using metals, and why in particular do we care about the sort of field of metal optics, and in particular why we might use metals in the mid-infrared. So I'll talk about some of our work in the mid-IR using sort of noble metals, traditional metals, the things that you guys would think of as metals that one might use in optics. So that's gold and silver and these sorts of things. And I'm going to talk about some of the challenges associated with using these traditional metals at these long wavelengths. And then I'm going to talk about our sort of recent work on how we decided and why we decided to basically make our own metals. Okay? And I'll talk about a number of different projects where we sort of looked at these designer metals and eventually moved towards nanoscale photonics using these types of materials, and then I'll end with conclusions. Okay, so why do we care about the mid-infrared? Well, there's a number of reasons why we care about the mid-infrared, and the first is that it's home to a wide range of sort of fundamental absorption resonances for a large number of molecules. So I'm showing some of these molecules here in this plot and where their absorption resonances lie in the mid-infrared. So when I talk about the mid-IR, I'm generally talking about wavelengths between 3 and 30 microns. There are official definitions for the different ranges in the mid-IR. I'm just going to say from 3 to 30 is what we consider the mid-IR to be. Okay, so if you look over here, you'll see the absorption spectra for ammonia. There's a couple things I want to point out in this absorption spectra. The first is you see that ammonia has these sort of distinct, narrow absorption lines. So oftentimes we call this the spectral fingerprint of a molecule, right? So every molecule has unique absorption lines associated with that molecule, and if you can see those lines, then you can detect the presence and ideally the quantity of that molecule in your system. The other thing that you might want to notice is that as you go from sort of the short wavelength side of things to the long wavelength side, you see a significant increase in the intensity or the strength of these absorption lines. And this is true for a wide number of molecules. It's not not just ammonia. I chose ammonia because ammonia is an important molecule for breath analysis. So for people who are looking at what we exhale and what that tells us about the functioning of our internal organs, ammonia is a key indicator for instance, liver and kidney function. Right? So people are really interested in doing trace gas sensing of ammonia in the mid-IR, for instance, for dialysis applications. Okay? So the sort of takeaway here is that we have strong, distinct absorption lines in the mid-IR, and that we can identify molecules using those absorption lines. Okay. Turns out that not only does everything absorb in the mid-IR, but then conversely, everything also emits in the mid-IR, in particular, any hot object. So unless you're at 0 Kelvin, you are emitting in the mid-IR right now, and my hope is that you are not at 0 Kelvin right now. So for instance, airplane engines or jets and sort of turbines, right? These all emit. They're very hot objects. They emit primarily in sort of the 3, or they peak in the 3 to 5 micron range. For biological objects such as us, our emission peaks in the 8 to 12 micron range. And so, of course, because I run a mid-IR photonics group, it's appropriate that the image I show of my group is a thermal image of the group. And I always argue that, or I always tell people that their heads are white hot because they're thinking so hard and expending so much energy. Except for that guy, I don't know what he's thinking about. So anyway, so if you're interested in tracking a hot object, and there are people who are, and these are good guys and bad guys, this is sort of the heat signature. These are the heat signatures that you want to latch onto, okay? Now, if there are bad guys who are trying to latch onto these heat signatures, then presumably there would be good guys who are trying to protect things that emit these heat signatures. So this is an example, it's about 2-3 years old, from BAE. They call it their adaptive technology. And if you go online, this is not classified information. And you can go online, you can actually find their YouTube video. And it's really cool. They have, I mean, I can't imagine how much of the government money they got to build this structure was used for this YouTube video, but I'm guessing a fair amount because the production quality is pretty awesome and it looks a lot like a James Bond sort of video with the music and the zoom shots and everything. Basically what they did is they took a car and they covered it in thermoelectric coolers, right? And these thermoelectric coolers are sort of, they call them pixels. They're obviously rather large pixels. They can take a thermal image of the background and then they can tune the temperature of their pixels to basically blend into the background. So this is a picture of the car taken with a thermal imaging camera. The car is still there, right? But now it's sort of changed the temperature on its surface to blend into the background, rendering it effectively invisible, okay? Now, this is really cool, and you'll be very impressed if you go and look at the video. But if you actually do a little bit of work and you look at how much energy is used to, for instance, change the temperature of a TEC by about 70 K, this is for a 1 by 1 centimeter region, it costs you about 10 watts. Now, it's possible that BAE has access to TEC coolers that are better than what I could find with a 10-second Google search. I'm sure they do. Nonetheless, we're talking about watts per square centimeter, which means that you might be able to effectively cool your tank for a short period of time. You will also at the same time roast anybody who's in the tank because you have to generate a fair amount of heat to do this, okay? So one of the things we're interested in is, so how can we control thermal properties of materials, right, on the nanoscale using very little amounts of energy and be able to do something like this, but without roasting anybody inside the tank. Okay. So everything, or a lot of things in sort of optics, are moving towards the nanoscale. And you can sort of see two very sort of simple examples here. If you want to detect the presence of ammonia atoms on the order of 4 angstroms. Right? Now, if you're looking for these sort of strong absorption resonances in the mid-IR, right, the wavelength of light that you're going to be using to detect the presence of ammonia is on the order of 10 microns. Right? There's a rather significant mismatch between the wavelength of your light and the thing you're trying to detect. Right? So that means that you're not going to have a particularly strong interaction between this molecule and the light that you're using to sense its presence. As we move towards sort of this new era of nanophotonics, where our emitters and our detectors and our optical components are moving to the nanoscale, right, we want to be able to design emitters or detectors that are on the nanoscale. But of course, if you're trying to design these sorts of emitters or detectors to detect 10 micron light, again, you have a real mismatch between the wavelength of your light right? And the size of the structures you're trying to get to interact with this light, whether it's to emit the light or whether it's to detect the light. Okay? So this is the primary thing that we're trying to work towards figuring out. How do we get our micron scale light to interact with nanoscale devices? And what you'll notice here, if you look at these sort of two recent examples of nano lasers, is that people use metal to do this. Okay? It turns out that we can use metal to essentially couple light to very, very small volumes, or to confine light to sub-wavelength regions. And that has to do with the optical properties of metal. All right? And so if we look at some sort of recent nanophotonic examples, so this is a slightly older one. This is basically what we call a solid immersion lens used to give patterning of photoresist, quote unquote, below the diffraction limit. Of course, it's not below the diffraction limit because you're using a lens. It's just a high index lens. And so you gain something because the wavelength of light is shorter in the lens, but ultimately you're not beating the diffraction limit here. Now, when you start to incorporate metal into your structures, then you can actually generate optical modes much, much sort of smaller than the free space wavelength of light. And so you end up with things like the hyperlens from the Berkeley group or plasmonic waveguiding structures. And I've listed sort of 2 references here. There are many, many others, right? So I'm going to talk about what these sort of plasmonic structures are and why they're able to confine light to the nanoscale. And then we're going to talk about why they don't work in the mid-IR at least. Okay, so just to sort of step back a little bit, I want to first remind everybody sort of where the optical properties of a metal come from, okay? So if we think about a metal in a sort of very simple picture, namely you have bound electrons that are tied to your atoms and you have free electrons that are sloshing around, then you can describe the interaction of an incident electromagnetic field in terms of the way that it affects these bound and free electrons. So you end up with essentially a background permittivity that comes from your bound electrons, and you end up with a portion of your permittivity that changes as a function of wavelength that comes from the free electron. So this is a very sort of simple way of looking at a metal. It's called the Drude formalism, but it actually works pretty darn well for a large number of metals across a wide range of wavelengths. Okay? So the key takeaway here is that the epsilon, the permittivity of a metal, results from the response of both free and bound carriers. Okay, so once we have the permittivity of our metal, let's look at a couple of modes that give us sub-wavelength confinement. All right, so these are plasmonic modes. The first one is a surface plasmon polariton. It is simply a solution to Maxwell's equation where you at the interface between a metal and a dielectric, you can extract the dispersion for this propagating mode, the surface plasmon polariton, simply by solving for Maxwell's equations. Right? And so this is a bound mode that can have sub-wavelength confinement, namely the penetration into the dielectric is less than the wavelength of the light, and it propagates on this metal surface. Okay? So what that means is you can use these types of plasmonic waveguides for exactly that, for waveguiding light. People have talked about using plasmonics for optical interconnects. They've talked about, again, because you're able to confine your light to a sub-wavelength dimension, they've used these for sort of enhanced sensitivity detection, and even displays. You can couple light into these propagating modes and funnel them through these sub-wavelength apertures, and they can act like filters, for instance. Okay. We can also talk about a localized surface plasmon. This is basically what happens when when light interacts with a sub-wavelength metal particle with a 3-dimensional geometry. In the sort of simplest case, when your metal particle is much, much smaller than the wavelength of light, you can make this quasi-static approximation. You assume that the electric field inside the particle is homogeneous, and you can solve your boundary conditions. And what you basically end up with is an external electric field that depends right here on this numerator, right? Epsilon of the metal plus some factor times epsilon of the surrounding dielectric. For a simple sphere, that factor is 2. And what that means is that you get this strongly enhanced electric field when the epsilon of your metal is equal to -2 times the epsilon of the surrounding dielectric. Okay, so this is a strongly localized mode that sits on a metallic nanoparticle. This is the mode that gives color to stained glass windows, right? And so this LSP mode is localized to sub-wavelength particles and can give you a strong enhancement of your field in the region of the sub-wavelength particle. So where do we see these sorts of things popping up? Surface enhanced Raman spectroscopy would be an example. You can get enhanced fluorescence. Some of the most interesting work using localized surface plasmons comes from medical imaging and photothermal cancer therapy. And the reason for that is because despite all of the hype that's gone into the fields of plasmonics and metamaterials, there's really one thing that plasmonics and metamaterials are very good at doing, and that is absorbing light. And unfortunately, in most instances, that's exactly the opposite of what you want these structures to do. But it turns out that there's actually some interesting stuff you can do if you leverage these losses, right? These losses are usually a big problem, but if you can actually turn that around and use these losses for something, then you can do some really interesting stuff. So for instance, what they've done here is they have metallic nanoparticles that they've functionalized to attach to cancer cells. And these metallic nanoparticles strongly interact with light of a certain resonant frequency as described by our localized surface plasmon expression. So when you hit those nanoparticles with the right frequency of light, they absorb that light and they get hot. And the idea is they essentially burn whatever cells they're attached to. This is work that's done by the Hollis group at Rice. And Naomi's also done some interesting work where she uses a similar nanoparticles and she puts them in water. And again, she hits them with light. They absorb that light and they actually locally boil the water and they create steam, but only in this sort of nanoscale region. So again, plasmonics and metamaterials are very exciting, but right now the thing they do best is absorb light. So that was sort of one of the things we got interested in the mid-infrared, because we know that in the mid-IR, this sort of thermal emission, this heat signature, can often be something we want to control, whether we want to hide a tank, or whether we want to shift thermal emission, or whether we want to make a lamp that emits in the mid-IR. Right, so for instance, in the near-IR, you can make what's called a perfect plasmonic absorber. It's basically a series of localized surface plasmon antennas that sits above a metallic ground plane, and you can get very, very strong absorption from these structures. And we can do a similar thing in the mid-infrared, and we can get basically perfect absorption at designed wavelengths. So we design our structures to absorb light 100%, which means that when we heat up our structures, they're going to selectively emit. Because in absorption resonance, when you flip the sample around essentially and you heat it up, that gives you a thermal emission resonance. Okay? So you can look at our 2D samples here where we've made structures that selectively emit at 5 microns. You can see this strong dip in the reflectivity. 1 minus the reflectivity should give us our emissivity. This is a measurement of essentially the background corrected thermal emission from our surface. And if you can make this type of structure and if you can turn on and off this resonance, then what that means is you can change the effective temperature of your surface, right? Because what you have is basically a very poor emitter except at 5 microns. And if you can turn on and off that 5 micron emission, then effectively you can make this very weak emitter look like a very high temperature object. Right? So you can talk about turning on and off thermal emission. You can talk about pushing emission into different wavelength ranges depending on where detectors work. Right? And so this change, being able to control that reflection dip can give you effectively 100 Kelvin change in the apparent surface temperature of your surface. And this is all done with essentially a surface that's less than 300 nanometers thick. So that is lambda over 20 or 30 at the wavelengths that we're talking about. And it turns out that you can actually change the thickness of this dielectric spacer layer, and you can effectively turn on and off this absorption resonance. And so there's some interest in our group in seeing how we can actually do this mechanically or in other ways where we can actually make what we call dynamic thermal skin. Now, this is all very interesting, but it's ultimately not what I really want to talk about today, because what I want to talk about are sort of plasmonic structures for sensing and for nanoscale application. So the question is, why do we care about plasmonics? Right? And I sort of answered this already. For our surface plasmon polaritons, these are the propagating modes. Right? People are interested in optical interconnects, enhanced sensing, and they interact strongly with sort of planar 2D geometries because, of course, they're tightly bound to the surface upon which they propagate. For the three-dimensional structures, or localized surface plasmon resonators, you get enhanced interaction with ultra-subwavelength molecules, or with detectors, or with light emitters. You get an enhancement of nonlinear effects, which of course just comes from the fact that you have strong electric field enhancement. and you can get localized absorption or heating for these photothermal applications. But almost all of the work I showed you, with the exception of the 2 slides on my group's work, all of this work on Plasmonics is done at short wavelengths. So it's worth asking why. But before we do that, all right, let's ask why we might care about doing this at longer wavelengths. Okay? So with these plasmonic structures, if we can get, for instance, 3-dimensional localization of light, we can get strong interaction with sub-wavelength elements, just like people argue for shorter wavelengths. So can we enhance the interaction of our 10-micron light with our ammonia molecules? Right? Remember I said one of the big problems of trying to sense these 4 angstrom molecules is that the wavelength of your light is many orders of magnitude larger. Okay? Right? Can we talk about sort of designing structures that selectively absorb? Again, leveraging the losses in plasmonic structures, and then can we turn those around and emit selectively? I've already showed you a couple of examples of our group's work on that. And for this, can we control the, and so this is one of the sort of things that we're moving towards right now, is can we control the interaction of light with nanoscale or sub-wavelength scale optoelectronic structures? Namely, can we integrate sort of a new generation of mid-IR plasmonics with sort of the existing mid-IR optoelectronic infrastructure and sort of develop smaller scale emitters, smaller scale detectors? Okay. So why is most of the plasmonics work done at shorter wavelengths? I want to give you one example here for the propagating surface plasmons and one example for the localized surface plasmons as we go from short wavelengths to long wavelengths. Right? So this is a work from the Spanish group where they look at what's called plasmonic beam steering. Okay, so the basic idea here is you come in with light from the top over here. It couples into this sub-wavelength waveguide, so not a lot of light gets through, but some gets through. And of course, some of that is emitted just in a sort of a cylindrical wavefront that you'd expect from a sub-wavelength aperture that's illuminated from this side. But some of it will, in fact, couple to these propagating modes on the surface of the structure. And as these modes propagate, they will scatter by these corrugations that are patterned into the plasmonic structure. So these corrugations will scatter light. Of course, that scattered light will interact with the directly transmitted light as well as the scattered light from the other corrugations and build up an interference pattern in the far field. Right? And so depending on the wavelength of the incident light and the geometry of your scatterers, you can in fact direct the light that's coming through this plasmonic beam steering structure. So we did similar work in the mid-infrared. We used we actually used 2 quantum cascade lasers. Obviously we had a bit of a gap here. Those are each like $40,000 lasers, so we just couldn't afford to fill in that short wavelength gap. But you basically see the same thing, right? So we built a structure that looks very much like this, and we see the sort of steering of the mid-IR light as we change the wavelength of our incident light. The Capasso group at Harvard put these sorts of structures on the facet of a mid-IR laser called a quantum cascade laser, and they're able to get very nice beaming from that laser facet. Okay, so again, as we go from the visible to the near IR, things look like they sort of hold up. Everything looks like it sort of makes sense. But I want to point out that the measurements we're doing to look at these structures are far field measurements. So we're looking at the beaming well away from the surface of the plasmonic structure. If we look at visible near IR, right, there's been tons and tons of papers on enhanced sensing with plasmons at sort of visible and near IR wavelengths. And generally what it boils down to is that people are looking at an index shift. So they're looking at the change in the refractive index in the near field of their plasmonic particle. Why is that? Well, first of all, it's because they don't have a lot of distinct absorption resonances for particles in that wavelength range. So what you generally do is you functionalize your localized surface plasmon structure, and then the analyte that you're interested in sensing bonds to that, and you can sort of see a shift in the near field refractive index around your structure. Right? And you can do similar things in the mid-IR. So this is an example from Hatice Altug's group, who was at BU, now is at EPFL. And she's using essentially what are mid-IR antenna structures. And again, these sort of collect the incident mid-IR light, and you can sort of see absorption resonances coming from those antenna structures. So we did sort of similar work with, again, our sort of perfect absorber type structures, but we're looking at a resonance in the material underlying our metallic disks. And we can see the sort of very strong anti-crossing. This is the location of a molecular absorption resonance. Okay. So the advantage of moving towards the mid-IR is that you can actually sense the individual absorption resonances as opposed to just sensing a refractive index change. But the disadvantage, if you look carefully, is that all of these structures are wavelength scale. These are antennas, effectively. Right? So antennas are, quarter wave, half wave antennas, but you're never going to be able to get sub-wavelength with a traditional metallic antenna in the mid-IR. And why is that? So why can't we go nanoscale with the mid-IR? The reason we can't go nanoscale is because we can scale the geometry of our structures, but we can't scale the permittivity of our metal. All right? So remember, I told you that localized surface plasmon resonance occurs when the epsilon of the metal is equal to -2 times the epsilon of our surrounding dielectric. Well, if we look over here at the permittivity of our metal, we can see that it goes to essentially negative thousands as we get to long wavelengths. Right? So what that effectively means is that our metal looks a lot like a perfect electrical conductor. Right? And unless you have some dielectric material, right, that has a epsilon of -2000 or -500, which I don't know of, you're not going to be able to get those localized ultra sub-wavelength resonances with a traditional metal at these long wavelengths. If we look at the propagating surface plasmons, what we see is that in the visible range, the black here is the dispersion relation for our propagating surface plasmon. You can see it really sort of moves away from the light line. This is the dispersion relation for just light propagating in a medium. Significantly, when you get to near the plasma frequency, you're sort of in this, again, in this wavelength range where the epsilon of your metal is negative but small. When you get to the mid-IR, your metal looks a lot like a perfect electrical conductor. And so really, your surface plasmon and your light line don't look any different. And what that means is that what you basically have is a very weakly bound light-like mode. It doesn't look at all like a surface plasmon mode. And you can see that if you look at two sort of parameters that define the propagating surface plasmon. The first is the penetration depth into the sort of dielectric. Remember, this is the big advantage of using a plasmonic waveguide, namely that penetration depth is ultra sub-wavelength. If you look at the penetration depth here, what you see, and this is normalized to wavelength even, is that we're looking at 10 times, at 10 microns, we're looking at 10 times the wavelength of light. So it means that your mode extends 100 microns, right? 10 times the wavelength. So that is, of course, not at all sub-wavelength. Now, the flip side of that is if you look at the propagation length goes to thousands of wavelengths. So these things are very weakly bound, but of course they propagate for very long distances because they don't interact with the metals. Right? So you don't have much of your mode that's inside the metal, which means that your losses are much, much lower. So that has some interesting aspects. Namely, you can take one of these beam steering structures, right? And now instead of just using sort of a periodic array to scatter light into one direction, you can start playing with the periodicity or the location of these scattering sites. And you can design these scattering sites to essentially build up your field in the proximity to the plasmonic structure. And so what we did here is we played around with aperiodic structures that allowed us to effectively design the electric field in the near field of our structure, right? Or in the sort of mid-field region. It's not technically near field, right? And the reason we can do that is because our light propagates for very, very long distances on these surfaces. And so we design structures that allow us to effectively focus light to positions either 250 or 500 microns. We can design where we focus the light. We can design beams that are all going in one direction or all going in the other or sort of curving. So we can actually play around with and build essentially the electric field from the transmitted light by using sort of interaction of large, large numbers of these scattering sites. If we try to scale our localized surface plasmon to the mid-IR, it's not even that it doesn't behave like the near-IR. You just can't do it. And again, the reason is this denominator here, right? You can't, the permittivity of your metal is just too large to be able to give you this sort of sub-wavelength localized surface plasmon resonance. You can make an antenna, but an antenna is a very different thing. An antenna is a wavelength scale structure. Okay. So let's see sort of where we are right now. Traditional metals allow for sub-wavelength confinement at short wavelengths. You can get enhanced sensing, although usually it's a refractive index shift. You can make nano optical electronic devices. You can do nanophotonic waveguides, but you have lots of losses. Now we can use those losses to make thermal emitters, right? And we can use antenna-like structures to do sensing in the mid-IR. but we can't go sub-wavelength, much less nano. Right? In order to go sub-wavelength, we need to be able to scale the properties of our metal from how they behave in the near IR or visible and make our metal behave the same way in the mid-IR at these long wavelengths. Okay? Now, I told you that we can describe the optical properties of metal using this Drude formalism. We describe the optical properties of metal by the bound electrons and the free electrons. Well, it turns out that we have a material system that I work with a lot where we have both bound and free electrons, and we can actually control the number of free electrons. It's a semiconductor. We can dope a semiconductor, and we can effectively put in the carriers that we want, and we can control the free carrier concentration in a semiconductor. And it turns out that if we choose the right semiconductor, namely if we choose a 3,5 semiconductor that has a low effective mass and that we can dope very highly, we can actually turn our semiconductor metallic in the mid-infrared. So what happens when we take a semiconductor that we dope very highly? So this is a indium arsenide structure. It's doped 3 × 10⁻⁹, which is actually quite high. We grow this by molecular beam epitaxy in my lab. And if we look at the sort of bulk transmission and reflection from this structure, what you see is that you get these sort of Fabry-Perot oscillations that come from the finite thickness of our indium arsenide. And you get essentially reflection on the order of 25–30%, which is what you'd expect from the surface of a semiconductor. But at some point, that reflection turns on. And you get near perfect reflection off the surface of your structure. That's when the surface becomes metallic, essentially. Right? So when the surface becomes metallic, it becomes highly reflecting. We can model this using that Drude formalism I discussed earlier. It matches pretty nicely. We can essentially talk about this plasma frequency. This is the wavelength of the frequency where our permittivity of our metal becomes negative. Right? And we can model the losses and this plasma frequency using the Drude formalism pretty nicely. Okay? And from that, we can extract the permittivity of our designer metal or engineered metal, whatever you want to call it, or kludged metal. Right? And what you see is that you can get both the real and the imaginary permittivity of the metal. And you can essentially determine where this material becomes metallic. And we can control that across a fairly wide range of wavelengths. This is for our indium arsenide structures. We can go from 17 down to about 5.5 microns. So it becomes, the epsilon becomes negative. We can actually look at the imaginary component of our permittivity, which is a good indicator of losses in these materials. And we can get much lower losses than you can with gold or silver at the equivalent plasma frequency. And the reason for that, of course, is that these materials are single crystalline. They're grown in ultra high vacuum, and so they're high quality materials. Right? They're not the sort of polycrystalline amorphous metallic structures. And we, of course, can control how metallic they are. One interesting side effect is that when I initially tell people that we can make metals out of indium arsenide, they say, well, that's great, but you have a limited wavelength range that you can play around with because indium arsenide is what's called a narrow band gap semiconductor, which means that, it has a very low energy band gap, and all light greater than that band gap gets absorbed. But what's really interesting is actually when you dope the heck out of these semiconductors, you're filling up the conduction band with electrons. And what that means is that you can't actually absorb light from the valence band to the conduction band if all those states are full. And what that means is that effectively our material becomes transparent out to telecom wavelengths. So that's a significant increase in the sort of usable frequency range that you have for this material system, because this is double. Essentially, you're doubling the band gap of your material. Okay. So before we start talking about what happens when our material becomes metallic, I want to give sort of one quick slide on something that we're working on right now, which is epsilon near zero material. So it turns out that you can get some really interesting effects when the permittivity of your material system goes to zero. When the permittivity of your material system goes to zero, you can effectively get ultra long wavelengths of excitations in the material. Right? And they basically, what happens is when you excite that material with a electromagnetic wave, typically we think about wave fronts propagating through a material, right? And you can sort of see those fronts if you sort of mark out the wave fronts. You can see those sort of propagating. In an epsilon near zero material, what actually happens is that your wavelength becomes infinite, right? And so the entire material sort of oscillates. The electric field of the material oscillates at the same time. So the electric field in your material is almost like a bulk excitation of your material. And it turns out that this type of excitation couples very nicely to the fundamental mode in a sub-wavelength waveguide. So what we did is we looked at transmission through ultra sub-wavelength slit, so about lambda over 10 or so. All right, and we looked at two different situations. One was an undoped, sort of high purity gallium arsenide material. So this has no material losses. So the only losses you're going to get come from essentially the fact that you can't squeeze light through a sub-wavelength slit. And then we looked at this material where we have our highly doped semiconductor. Now, of course, the highly doped semiconductor, when you introduce all those carriers, you're introducing a lot of losses. But it turns out, actually, that at the E and Z frequency, so at the frequency where your epsilon of that material is equal to 0, you can actually see this very strong, very distinct transmission peak. And when you compare it to the transmission through the sort of lossless material, where the only losses are geometric losses, it's actually a significant improvement. And you get this improvement, so gallium arsenide is sort of the best case scenario. You get this improvement for sort of a wide range of slits, and it gets stronger as you go to smaller and smaller slits. Okay, so that's sort of a little bit of an aside. What I want to talk about is what happens when our materials become metallic, essentially. So if you remember when I showed you the two sort of adjacent slides where I talked about what happens when you go from visible near IR to mid-IR, I said that in the far field, things look very similar, right? Things, if you measure these structures far away from the actual surface, right, the optical properties of the materials look very, very similar. It's only when you get down near the surface that you start to see these really big differences. When you see the extra long propagation length of your surface plasmon, when you see, in fact, that the localization of your electromagnetic field can't be sub-wavelength. So it's only in the sort of near field where you see these differences. So what we did is we basically made an array of micron scale pucks. So this is, again, sub-wavelength structures. And we did see a absorption resonance, essentially. So it ends up being a dip in reflection and a dip in transmission associated with the patterned surface. So we took our metallic structures, or our metallic surface, we patterned it into sub-wavelength features designed to sort of mimic these localized surface plasmon structures. And we see, in fact, a dip in the reflection and the transmission, indicating an absorption resonance. In collaboration with the King Group in the Mechanical Science and Engineering Department, we decided that, well, just seeing that dip isn't a good enough indicator, because we know that in the far field, when you do a transmission or a reflection measurement, of course your measurement is in the far field. You're not looking right up at the near field of your structures. We need to show in the near field that we, in fact, have this localized absorption resonance. So we collaborated with the King Group, and they use this IR AFM technique. Namely, they put an AFM tip very close to the surface. They shine a laser up from the bottom of a material, which actually required a somewhat complicated substrate release and then attachment to a zinc cell prism that my postdoc Stephanie did quite nicely. And so they shine the laser up from the bottom, and of course, when you get sort of an absorption resonance, right, that light is converted into heat, and you get a thermal expansion, and that will deflect the AFM cantilever, and you can detect that deflection, and you can detect, therefore, the amount of heating with nanometer scale precision in these structures. And so if we look at now this is not an AFM scan, this is essentially a localized heating scan with about 100 nanometer resolution. What you can see, in fact, is that you get very, very sort of sharp heating resonances associated with these microparticles. And in fact, if you look, the electric field for our incident light is horizontal, and you do see essentially this strong heating along the edges of your microparticles. So not only are we able to sort of observe in the near field this absorption of the sort of localized surface plasmon resonance, but we may actually even be seeing some indication of the actual shape of the mode on our microresonator. So we can look on resonance and we can look off resonance, and of course it lights up on resonance, but when you're not on that absorption resonance, you don't see a very strong absorption. You see some effects that probably come from geometry. We can look at the topography, of course, at the same time, because this is, in fact, an AFM tip. And we can model these structures, and we sort of see a reasonably good approximation of our experimental results using three-dimensional COMSOL modeling of our structures. So we may, not only are we able to see the sort of localized mode in the near field, but we're actually might be able to actually image the heating and therefore the optical mode in our structures. We wanted to go one step further. Again, I said that the sort of point of this talk was to sort of demonstrate how we can take things with micron scale or micrometer scale optical resonances and shrink them down into nanovolumes. So those structures I just showed you were micron size. They were fairly thick. They were designed to absorb light resonantly. But ultimately, if you want to make a sensing structure, you don't want the thing that's supposed to enhance your sensing. You don't want that doing all of the absorbing. Right? You want the molecules that you're trying to sense to do the absorbing. So what we need to design is a structure that's able to confine your electric field, but without dominating the absorption of that mode. And so we basically just went with significantly thinner structures, so it cut down on our absorption significantly, but still gave us an enhancement of the electric field. And we fabricated these templates of these structures using nanosphere lithography. That can give us, it's a cheap way of basically covering an entire wafer with a quasi-periodic array of nanospheres that we can then use as an etch mask, and we use those to define essentially these nano antennas. Right? So these are nanoscale objects about 400 nanometers in diameter that are designed to interact strongly with long wavelength, 10 micron, 11 micron light. Right? In fact, if you think about it, you could pattern a dielectric or a metallic surface with this periodicity, and if you shine mid-IR light on it, it shouldn't be able to tell. It shouldn't be able to see structures of this size. It's much, much smaller than the wavelength. You'll essentially see an effective medium response, but you're not going to see any sort of localized resonances coming from this scale of patterning. But when you dope the structures, in fact, what you see are very strong resonances. So if we look on the left side here, what you see is a rather broad, but nonetheless a rather strong reflection, which is indicative of an antenna resonance. And so the dotted lines here are COMSOL models. The solid lines are experimental models for two different samples with different dopings. Right? Remember, I said that one of the nice things about making our own metals is that we can control the plasma frequency of the metal. So we can actually shift where it becomes metallic, and therefore we can essentially tune where these antennas of the same dimensions, where these antennas have their resonant peaks. Okay? And so if we compare any set of antennas in the two different material systems to a undoped sample that has been fabricated in the exact same way, so the same geometry structures have been fabricated, you can see that, again, this behaves exactly as you'd expect a semiconductor surface to behave. 30% reflectivity, no reflection peaks or any sort of resonances that can be observed. Right? But when you use the doped surface, when you make these nano antennas, you in fact see these sort of rather strong resonances. So when we coat the structure with a very, very weakly absorbing polymer, in this case it was PMMA, so we have very weak absorption lines that overlap with our antenna resonances, and a very thin layer of PMMA in the first place. So only 50 nanometers, again, much, much, much smaller than the wavelength of the light, to the extent that you would not expect a strong interaction between a 50 nanometer layer and 11 micron light. Right? What you see, in fact, are rather significant dips in your reflection. Okay? And you see some of those maybe showing up in the coated control sample, but realistically they're much clearer, much stronger when you're sitting on the resonance of your nano antennas. Right? So here you have a fair amount of noise. You can't pull the absorption signals out of the noise. If we do a division by the uncoated, it just ends up looking like a mess. It's just a noisy structure. But here we can sort of clearly see these absorption resonances pulled out of the reflectivity. We can also, of course, because these are grown by MBE, we can make multi-layer structures. So we can grow metals and then dielectrics and then metals. And this is a work that is currently under review. It should come out in a couple of weeks is the hope. But basically we can design structures to couple light into these sort of ultra small waveguides. So this would be an undoped indium arsenide waveguide that's sort of sandwiched by a patterned metallic layer and over a metallic ground plane. And what you see are these very, very strong absorption resonances that correspond to coupling into these sort of propagating modes. It turns out these propagating modes are kind of interesting. They have a negative index associated with those modes. But what that basically means is that these are sort of narrow absorption resonances where you get highly confined light in the region underneath or in the undoped structure. And these effectively act like photonic crystals, or plasmonic crystals, excuse me. It's a little bit complicated. I don't have time to go into it since I'm running a little bit out of time, but if you're interested, I'd be happy to talk to you about this later. Okay, I have a couple of minutes before I run out of time. And I want to talk about, I basically want to undercut my entire talk at this point. So, up to now, I've tried to sell you on this idea of mid-IR plasmonics and how exciting it is, and this sort of this new field of metamaterials that, well, I guess is not so new anymore. But there's some really exciting things that we can do with metamaterials. But as I mentioned before, for most practical purposes, what metamaterials are very good at doing is absorbing light, and it's hard to make, for instance, a cloak for a spaceship, an invisibility cloak for a spaceship, or for Harry Potter, whoever you're trying to make it for, if you have a surface that essentially absorbs 90% of your light. So that doesn't do you much good for cloaking purposes. So I was thinking about sort of these sort of newfangled fields that pop up and that give us all research funding for a few years before they eventually die off, and sort of traditional sort of optics that we all sort of learn in our first optics course. So I want to talk a little bit about metamaterials versus a simple thin film interference effect. Okay. In particular, I want to frame this in terms of this sort of iconic scene from Indiana Jones. I don't know if you remember this, right? But the Indy's in the square, and this guy shows up. He's a really great swordsman. He's got all sorts of crazy moves, and we all know what happens next. What does Indy have? He has a gun, which is not particularly exciting, but this is what ends up happening. So the sort of argument I make is that, okay, maybe metamaterials are very, very cool, and maybe they're very, very exciting, and they look really cool like our swordsmen, but ultimately, sometimes the tried and true is in fact that tried and true. So I want to give you an example of this. This is the thin film interference. When you have a soap bubble, right, and it has those different colors in it, right, that is nothing more than a thin film interference effect, right? Light is partially reflected. It gets into the thin film of soap. It bounces back and forth. You get destructive and constructive interference depending on thickness and shape and these sorts of things. Okay, so let's look at a couple of examples here. So here we have a thin film of a relatively lossless dielectric that we put on top of a metallic, a highly reflecting substrate, right? And so because this thin film has some losses, right, basically what you get is you get an absorption dip when the thickness of the film is equal to lambda over 4. So basically what happens is the light sort of bounces around. You get a destructive interference effect, and the light that is destructively, or what light that isn't reflected is of course absorbed in this lambda over 4 layer. Okay, so nothing particularly complicated here. So recently, the group at Harvard showed that, well, you can take a very thin, highly absorbing layer, right? And you can do the sort of same, you get the same sort of absorption resonance, right? But and you don't need the lambda over 4. You can actually go much thinner than lambda over 4. And the reason, of course, is that this lambda over 4 comes from essentially the pi phase shift that you get at the air dielectric interface and at the dielectric gold interface. But if you play around with that phase shift, then you can effectively shorten the thickness of your top layer, right, by essentially having a non-pi phase shift at that dielectric interface. Now, of course, when you introduce losses, you have an imaginary component to your epsilon, you have an imaginary component to your refractive index. And so when you do Fresnel's law, you get an imaginary component that's essentially a phase shift, that's a non-pi phase shift for this interface. So we've been working on something similar, right? So this is the work from the Harvard group. We've been working on something similar, but instead of using a lossy dielectric, we went back to the idea of using a lossless dielectric because we like the idea that we can, when we put our dielectric on our material, we know what it does. Right? We know that it has this refractive index and it has no losses. Right? And we want to be able to control that. If you're using, as they were here, germanium above the band gap of germanium for visible light, that's tough to work with. Those losses are large. It's hard to know exactly what they are. So we used, again, germanium, but it's lossless in the wavelength range that we're working. And we used a doped semiconductor instead. Now, when we play around with the doped semiconductors, as I've mentioned before, we can control the permittivity of our semiconductor by controlling the doping. So in this case, we were using doped silicon that we simply dope by using a spin-on dopant layer. Right? So we are able to control where the epsilon of our metal becomes negative. And in fact, by doing that, we can operate in this regime that's very close to the epsilon equals 0 regime. And when we have epsilon equals 0 or close to 0, we can get very large shifts in the phase shift. So shifts away from the pi phase shift at this interface and towards essentially a 0 phase shift at the interface between our doped semiconductor and our lossless dielectric. And we can get very strong absorption with thicknesses much, much less than the wavelength of light. And in fact, this is what we did. So this is what our doped semiconductor looks like. Again, it has a sort of characteristic response that I've already showed you, where it goes from being sort of marginally reflective to highly reflective as you go to long wavelengths. When we put a very thin layer of germanium, in this case about 165 nanometers, which is, of course, significantly less than the wavelength of light, we basically get near perfect absorption. And again, this perfect absorption comes from the fact that we're able to control the phase shift at the interface between our doped semiconductor and our germanium. We can play with the thickness, and we can change that absorption resonance all the way from basically under 4 microns out to 12.5 microns. This is a largely angle insensitive and polarization insensitive response. So you see that you don't see much of a shift. Right? So what that means is that no matter what wavelength you're coming into, or excuse me, no matter what angle or polarization you use coming into the sample, you basically get the same absorption resonance. And when we then heat these structures up, this would be the sort of modeled thermal emission that we would expect. And this is the actual thermal emission that we obtain. So you see that these are also, again, if we can design absorption resonances, that means we can design thermal emission resonances. So this is our model. Again, simple model. It's just a simple transmission matrix model. And this is the experimental results. And of course, we can pattern this stuff in order to make cool things like the Illinois Eye. So I think the pizza showed up, so I'm pretty sure I'm losing your attention exponentially. So I'll end with conclusions. I talked a little bit about mid-IR plasmonics with traditional metals. The problem here is that we have very weak confinement. We have long propagation lengths, which we can use for some neat things. But overall, if we want to take the mid-IR nano, we can't do it with traditional metals, right? We can control beam steering or beam shaping. We can design absorption resonances, but we can't do anything on the nanoscale. So if we move to our designer metals, now all of a sudden we can start accessing the nanoscale. These metals are crystalline, they're low loss, they're high quality. They're, in fact, if you want to think about it this way, they're purer than the traditional metals that we use. When you deal with gold and you deal with silver, those have inner band absorption resonances near the plasma frequency. You can't model them with a perfect Drude model near these sort of interesting wavelength ranges where epsilon goes to 0. In our materials, you can. Our Drude model holds solid for a wide range, and especially across the epsilon near 0 range. So we have sort of a new sort of set of physics that we can work with that one can't really access with gold or silver. And in addition, of course, we can grow these with sort of atomic precision. We can integrate them ideally, and this is the next step with semiconductor devices. We can grow layered materials. And we've shown that we can support mid-IR localized surface plasmon resonances, and we can use that to enhance IR sensing. And we can also, as the sort of last thing I showed, they can be used as lossy metals, essentially for this ultra-thin film absorption and emission, which is, again, the thin film resonance. So if you're interested in this sort of stuff, we did a review paper for nanophotonics this past year that covers a lot of sort of things that I talked about today. And I think with that, I will end. And if anyone has questions, I'd be happy to take them. Thank you. Yes?
I mean, obviously, the way, sort of keep things great, addressable mission. Do you see some way of putting this on, say, an emitting transistor or something like that in a form that we can get, some sort of addressable, controllable mission?
So that's a really good question. And ultimately, yes, of course, we are interested in that, although I don't know of any light emitting transistors at this wavelength range. But yes, sort of the idea of going to sort of a nanoscale mid-IR emitter is, of course, very intriguing. Right now, the first step before we get there is to get some understanding of how these sorts of localized resonances interact with electronic resonances, right? Because ultimately your light is emitted or detected from an electronic resonance and usually a heterostructure material. So we can do that. We can grow optoelectronic devices that have designed resonances in the sort of the range where our antennas are especially interesting. So first getting an understanding of the sort of physical relationship or sort of what happens at that near field interaction, that's sort of the first step. But then yes, the next step is looking at detectors, and then emitters are harder, but yeah, ultimately that would certainly be of interest. So yes.
By some way of, say, controlling the doping, I mean, is that the...
That's right. So I mean, again, these things are epitaxially grown, so we can grow a layer that we would sort of consider our antenna layer, right? And if we put that close enough to an emitter layer, right, then the idea is to try and look at how you can get some strong interaction between those two and maybe enhance. Maybe. There's been a lot of interesting recent work that people are trying very hard to ignore that suggests that this whole concept of sort of sub-wavelength nanoplasmonic lasers is sort of a load of, it's not feasible at the nanoscale simply because if you want to make a electrically driven light emitter, you have to dump a lot of current into a nanoscale volume. We may actually have some advantages, namely we can be very sub-wavelength, but still much larger. We can be on the sort of the hundreds of nanometers as opposed to the 50 or tens of nanometers. So then we might not be fighting the same sort of current density limitations. So I haven't seen any work that suggests it couldn't be done at these long wavelengths, but there are obviously other complications. Are there any other questions? Nope.
Okay, any more questions? If not, let's thank our speaker again.